Welcome back, folks. Next, I want to talk about reflections. So that's if I want to take a graph and flip it. So for example, I could take the square root graph here. And there's two kinds of reflection, horizontal and vertical. I could put a mirror right here and look at the image of this graph in the mirror. What that would give me is this reflection here. That's called a horizontal flip. Or I could put a mirror on the ground, like a puddle. We could look at our reflection in the puddle. So that's flipping over upside down instead of left to right. We call this one a vertical flip. Mirror on the wall, puddle on the ground. Those are the two kinds of reflections we'll tackle in this class. And the way I want to think of these is if this is the point 4, 2, there's going to be a point that corresponds to that over here, and we're going to have a reflection of that point down here. What are their coordinates going to be? Let's take a look at this vertical one first. Look at it this way. It's the same distance left or right. They're both on this vertical line, right? That's what I mean when I say this is the reflection of that. If your nose is here, the reflection of your nose is going to be down here. So they're the same distance to the right, but as far as the up and down distance goes, this one's 2 above. So for this to be symmetric, this one has to be 2 below the axis. So this has to be the point 4, -2. It's still 4 units to the right, but now it's 2 units down instead of 2 units up. Does that make sense? Why am I asking this? This is a recording. I can't ask a recording if this makes sense. Hopefully that makes sense. I'm going to do the same thing again. If the mirror's on your wall, your nose isn't going to be any higher or lower in your reflection. It's going to be the same distance up and down, so the y-coordinate's still going to be 2. But now it looks like it's going into the wall instead of out from the wall. So the x-coordinate of your reflection is going to be flipped. Instead of being 4 feet away in front of the mirror, it's going to look like it's sitting 4 feet behind the mirror. So this is going to be a -4. So to get a vertical flip, we make the y-coordinate opposite. To make a horizontal flip, we make the x-coordinate opposite. So think for a moment about how we would do that. Second, I need to get a little natural light in here. Let me open the drapes. Okay, that's a little bit better. Getting a little eye strain. I have to record a lot of these today. Don't want that. So, have you thought about how we might change the inputs or the outputs? Oops, gave it away, didn't I? If I want to make the y-coordinate flip, all I'm doing is making the output negative. So if that's the graph, if f of x equals the square root of x, then to get a vertical flip, all I have to do is take this output and make it negative. So I'd call this h of x, it's going to be negative f of x. Whatever output we have, it'll be negative. In this case, that would just be negative square root of x. So that's our vertical flip. For our horizontal flip, look at this. It's the x-coordinate that changed, so the input needs to go negative. So I'm going to call that one g of x, and it's going to be f of negative x. In this case, that would be the square root of negative x. So you should be seeing a pattern. Horizontal transformations are always on the inside of the function. Vertical transformations are always on the outside of the function, because a vertical transformation is just going to change the y-coordinate, the output. A horizontal transformation is just going to change the x-coordinate, which is the input. So that's how we do a vertical flip. And every point is going to get reflected over the axis the same way. So if this is the point 1, 1, when I do a vertical flip, I say h of 1, this is the point 1, 1, h of 1 is just negative f of 1. So it's negative of the square root of 1. So h of 1 will be negative 1 for the same reason that f of 1 is positive 1. It's just the same thing, but with an opposite y-coordinate. So that flips over to 1, comma, -1. Whereas if I want g, I can't take g of 1. If I plug a 1 into g, I'm going to get the square root of -1, which is I, and we don't do complex numbers when we're working with functions in this class. So I can't take g of +1. But if I take g of -1, I get the square root of -1, which is the square root of 1, which is 1. So g of -1 is the same as f of +1. So we have -1, 1 right here, for the same reason that +1, 1 is right here. So every point gets flipped over the axis, and that's a reflection. Here's one more thing we can do with reflections. What if I want this curve right here? How would I get that? I could do a horizontal flip to get to the blue curve, and then if I do a vertical flip after, the blue curve turns into the red curve. So I could do a horizontal flip and then a vertical flip. Now, on the other hand, if I do a flip down to the green curve, a vertical flip first, then all I need to do is a horizontal flip to get to the red curve. So either one will work, but it's both flips. So this red curve here, I could call it k of x, and it's going to be made from f of x, but I'm going to do two things to it. I need to do a horizontal flip and put a minus sign right here. And then I need to do a vertical flip, and that puts a minus sign right here. So if I take k of -4, that's negative f of -4. So the first thing that's going to happen is that these minus signs cancel out. So the minus sign flips the input. This is negative f of +4. And then the second minus sign flips the output, which was 2, now is -2. So this is the point -4, -2. But there's one other way you could think of this red curve, and that's if this whole graph were a wheel and the axle was coming right through the origin, picture turning the wheel, right? This whole graph is spinning. If you rotate this graph halfway around, the red curve lines up with the black curve, and the blue curve lines up with the green curve. If you rotate 180 degrees, so if you do a horizontal flip plus a vertical flip, you get 180 degrees of rotation. Now that actually pays off in a big way because I want to talk a little bit about symmetry. So there are some functions that we've dealt with in this class, like y equals x squared, that have a natural kind of symmetry. If I put a mirror right down the y-axis, right down the middle of the graph, this graph is the same as its reflection. It looks the same on both sides. So this is a very basic geometric form of symmetry. We call this horizontal symmetry. And a way we can test for it, if you look at the graph, of course, you can see that it's the same thing reflected both ways. But if you just have the algebra and you want to know if there's horizontal symmetry, a way we could see it is, let's call this f of x. If I do a horizontal flip, then I'd make my new function, let's call it g of x. I'd make it like this, f of -x. That's going to flip the inputs, flip it over this y-axis. So that's a horizontal reflection. But take a look at the formula. F of x is x squared, so g of x just says plug a -x into f. So it's going to be -x gets plugged in, and then it gets squared. But what happens when you square a negative number? This is just negative x times negative x. Well, the minus signs cancel out. So g of x is actually the same as x squared. But that's the same as f of x. So we can see that this is a horizontal flip or we can see that this graph has horizontal symmetry because when I did a horizontal flip, nothing changed. So there's another kind of symmetry I want to talk about. Before I do, I just want to point out, there's another kind of symmetry I want to talk about. Okay. You might be thinking like, well, what about vertical symmetry, right? The problem with vertical symmetry, so let's say I draw this and it's vertically symmetric. Its reflection in the puddle is the same graph. Why is this bad? Because of the vertical line test. A function has one output for every input, but if you have vertical symmetry, you've got at least two. So this is not a function. So vertical symmetry is bust. Well, what are we left with? What else could we have? Look back at my original diagram here. We could have this third kind. We could have a rotation and be symmetric. And that's perfectly acceptable. So, as an example, let's say that h of x, let's say that that's, x cubed. You remember the toolkit graph? It looks like this on the right, and it looks like this on the left. If you spin this around like a pinwheel, you get the same function when you've spun it halfway around. So we call that rotational symmetry. And the way I could test for it is if I rotate 180 degrees, I should get the same graph. I should get the same function. Well, how do we do that? Rotate 180 degrees. That'd be h of negative x for the horizontal flip, and then I also have to do a vertical flip. So I'd be saying negative h of negative x equals h of x. Now up here, with the horizontal symmetry, the test for this one was if I did a horizontal flip, there was no change. So I'm saying f of negative x equals, f of negative x equals f of x. So I can combine these into one mega test. What I can do is say, well, this one's f of negative x, and this one's negative h of negative x. But what I'm going to do is I'm going to say, let's multiply both sides by -1. H of negative x equals negative h of x. So I'm saying, whether I do a horizontal flip or a vertical flip, I get the same result. Take a look at this graph. If I do a horizontal flip over the mirror on the wall, I get the, I get this blue curve. Jeez, can't draw today. If I do a horizontal flip over the mirror on the wall, I get this blue curve. On the other hand, if I do a vertical flip over this puddle on the floor, I get the same blue curve. So a horizontal flip is the same as a vertical flip, and that's because the graph has rotational symmetry. So my test is going to be, this is my test for rotational or horizontal symmetry. To test f of x, if f of negative x equals f of x, our symmetry is horizontal. And if f of negative x equals negative f of x, our symmetry is rotational. And if it equals something else, then it has neither kind of symmetry. Plenty of functions have neither kind of symmetry, like the square root. There's another name for these that I'd like to share with you now. And let me show you the reason for the name. If I graph x squared looks like this. Oops. So here's y equals x squared, or let me call it f of x. And let's say I also do x to the fourth. That looks a bit like this. Or let's say I do x to the sixth, and that's even steeper. Flatter on the bottom, steeper everywhere else. So this is h of x equals x to the sixth. Well, these all have something in common, and that's that if I do the symmetry test, f of negative x equals negative x all squared. So it's negative x times negative x. And like I showed you before, all the minus signs cancel out, and I just get x squared again. So f of negative x is the same as f of x. If I do a horizontal flip, nothing else changes. But look at these other functions. They clearly have the same kind of symmetry. And what's going on under the surface is if I take g of negative x, I'm going to get negative x to the fourth, which is negative x times negative x times negative x times negative x. Well, this pair of minus signs cancels out, and this pair of minus signs cancels out. So all that's left is x to the fourth. And with x to the sixth, there'd be three pairs of minus signs that cancel out. So the trick is, as long as I have an even number of minus signs to cancel out, as long as I've got an even power here, I'm going to get the same function back. So x squared and x to the fourth and x to the sixth, for that reason, any function with horizontal symmetry is called an even function. And it's actually exactly the same circumstance for these functions. Here's x, and here's x cubed. And this one's flatter on the center and steeper on the edges. Here's x to the fifth. And these all have rotational symmetry. And we call them odd functions. Notice that all the powers are odd? Well, here's what happens. If f of x were x cubed, let's say, and I try the test, f of negative x is going to be negative x times negative x times negative x. One moment. Having a hard time getting comfortable today. F of x is negative x times negative x times negative x. Two of the minus signs cancel out, but we get stuck with the third one. So we're going to end up with negative of x cubed. So f of negative x equals negative f of x, which is the test for rotational symmetry. So if it were x to the fifth, there would be two pairs of minus signs that cancel out, and then the fifth minus sign is stuck, or x to the seventh, or x to the 11th. Those are all odd functions, and they all have rotational symmetry. So we call any of these even functions, and we call any function with rotational symmetry an odd function. So this is often called the even or odd test. Now, of course, again, it's possible for a function to be neither. So let's take a look at some example functions. Here's f of x equals x cubed minus x. Now you can see from the graph, but if I didn't have the graph, I'd want to know, is this even or odd or neither? Let's try f of negative x. It's negative x cubed minus negative x. So I've put a negative x everywhere that x used to be. Well, negative x cubed, like I saw up here, that is negative of x cubed. Two of the minus signs cancel out, the third one stays. And minus a negative x is just the same as plus x. So f of negative x is negative x cubed plus x. But as a matter of fact, that's the same as negative 1 times x cubed minus x. I can factor out a minus 1, which is negative of f of x. So f of negative x equals negative f of x. Therefore, this function is odd. And then if I were graphing the function, I could plot some points over here on the right. See, it goes like this. And then I don't have to plot any points on the left. I can just say it's an odd function. So I'll take this whole thing, rotate it 180 degrees, and the rest of the graph has to look like this. So it saves you some time when you're drawing the graph. Or if I had g of x equals x to the fourth plus the absolute value of x. If I take g of negative x, that's going to be negative x to the fourth plus the absolute value of negative x. Well, negative x to the fourth, that's minus x times minus x times minus x times minus x. Just like we saw up here. All of those minus signs are going to cancel out, and we'll just get x to the fourth again. So this first term here is just x to the fourth again. Now what's the absolute value of minus x? Well, absolute value doesn't care about negative signs. It drops them, in fact. So this is the same as the absolute value of x. So g of negative x is exactly the same as g of positive x. So this must be an even function. So when I'm plotting the graph, I can plug in some points and see that on the right-hand side, it seems to go like this. And then I don't have to plot any points on the left-hand side. I can just say the left-hand side must be symmetric. If I draw a mirror on the y-axis, and it's pointy down here at the bottom. It's just a little bit pointy because I know that it's symmetric. So that's how I can graph g. And of course, some functions are neither one. So if I said h of x is 3x cubed minus x squared, well, h of negative x would be 3 times negative x cubed minus negative x squared, which is negative 3x cubed minus x squared. And that's not the same as h of x, because this term's negative. But it's not the same as negative h of x. Negative h of x would be negative 3x cubed plus x squared. Minus sign goes to both terms. So this isn't the same as either one, so it's not even and it's not odd. And when I graph the function, sure enough, it looks something like this. It doesn't have rotational symmetry about the origin, and it doesn't have horizontal symmetry about the y-axis. So that's symmetry, and it comes from our discussion of vertical and horizontal flips. I've got a couple more videos in this series. Next, I'll tell you about stretches and shrinks.